So again, hello everyone, and thank you for having me. Recently, I have been focused on automating visual inspection, in particular on anomaly detection, and I'm going to present our latest research on this subject. It will be mostly around the paper me and my co-authors published this summer on one workshop at CVPR, and I will refer to this paper as our benchmark. I also want to thank my co-authors for their time and contribution. I will start with About Me section. This is a photo with our poster for another paper from CVPR 24. I am on the right, and I'm afraid I was not that good at that meme, but my co-author nailed it. I studied at Czech Technical University, and during study I was working as a research intern at the drone lab at the uni. But compared, I think, to the rest of talks, this talk won't be about robotics. So yeah. Currently, I work as a research engineer at Valeo, and for the context, Valeo produces different car parts, and that's why we will discuss automatic visual inspection. You can find me using my name at the platforms below. Here's the content of the talk. I will start with the general definition of visual inspection and anomaly detection in particular, and explain why it's so important. And next, we will discuss academia-industry gap we have identified in our benchmark paper, from datasets to metrics and models, and especially evaluation settings. And after this, I will go into more details on experiments we had in the same paper and conclusions we can make from them. And number 4, the best practices. I can say that important intent of this speech is to provide some kind of guidance to people who are new to visual industrial anomaly detection and explain what you can do and which things you should be aware of. And last one, just quick conclusion. So yeah, I will start with a quick overview of the subject. The target of anomaly detection is, to detect anomalies or defects in case of visual inspection in manufacturing. And usually during training, we are given only normal images in green on the right picture, and based on them, we should be able to identify tiny differences like cracks or scratches in the new data. And tiny is the important part. Overall, image can look normal, especially from a first glance, and this is the main difference with the more common out-of-distribution task. I guess everyone can see why elephant is out of a distribution on the left, but on the right, if you can see, the problem is the tiny crack at the bottom of a normal image. I think it's much less obvious. And by the way, yeah, it is also a quite hard task for humans as well. Some estimates show that human operator can overlook up to 25% of specific defect types. You can see the second reference on this slide for the more data. And of course, missed defects shipped to customers. They cost industries billions annually in recalls, warranty claims, and even brand damage. And why we even need anomaly detection for this in particular? Why not to train just a supervised classification model? The answer is we never would have all the defects available during training. For some defect types, we can have literally 5 photos collected over a year-long period. And also entirely new defects can just emerge one day. And if you cannot detect them, they will be shipped to customers. Yeah, and on this slide, normal image is in green for reference, abnormal image is in red, and if you trained your classification model only, let's say, to detect scratches, it might even not recognize this new defect with all the parts missing because there is no scratches. So we cannot really train anything supervised which is not able to detect new types of anomalies. you might sometimes have a combination of supervised classification model for some common defects, for which you have enough data, but you still need anomaly detection model to detect rare and unseen defects. Yeah, just to summarize it, anomaly detection task is quite important for automating visual inspection, and there are many AI models emerging very often which promise to solve this task and classify 99.9% of parts correctly. And here we come to the main topic of our benchmark paper, a concerning gap between academic research and industrial implementation. You find a modern state-of-the-art model which performs almost perfectly on a popular dataset, and you run it on your data, and it performs really poorly and is basically useless for you. And here on this slide is an example of two recent state-of-the-art models, GLASS and SimpleNet, getting more than 99% out of 100% of our work. But when we use a less popular industrial dataset, the second and the third row, the performance drops strongly to just 90% for one of the datasets and 80 and even 70% for another, which is quite useless, I need to say. So yeah, here we'll talk about academia industry gap. And yes, sorry about the missing visualization. I just found out that papers with code website is gone. And yes, it's actually quite sad. But in any case, if you follow new research in this area, you can see that visual anomaly detection has quite exploded in recent years. But what has it brought us? Let's start with datasets. Most of the popular datasets, such as MVTech ID or VISA, are produced in the laboratory settings. Authors take real objects and damage them manually to imitate defects. In 2019, it was a huge step forward when MVTech ID dataset emerged and researchers were able to work with rather complex objects with realistic-looking defects comparing to older datasets. You can see example on the left, and MVTech ID is on the right. Yeah, I think it's quite obvious it was an improvement. But the problem is that datasets have not changed much since that time. We still have an object which, to be fair, can be center cropped without any defects missed, too much background. We have 3, 4, 5 types of manually created defects, which are usually similar across categories of objects and even datasets. On the contrary, real-world datasets with defects emerging naturally during the manufacturing process provide wide variety of defects. It can be more than 20 types of defects in some particular datasets. And at the same time, more practical crop settings, you cannot crop the images feature without missing defects. And also, unfortunately, many fewer categories of objects because it is hard to get a permission to release real production data. And to mention MVTech ID again, another important thing is that many papers still claim state-of-the-art on this dataset. And as I shown earlier, papers compete on just last 10th of percent classified correctly. So it's, yeah, this particular dataset, MVTech ID, is being overfit quite strongly. And as our benchmark shows, better results on MVTech ID not necessarily correlate with better results on other datasets. And just a bit of terminology, most popular datasets contain only structural defects, like scratches, cracks, some kind of surface damage. But it's also important to understand that if we can detect another type of defect, logical, which can be missing components, or maybe wrong shape, or maybe even wrong relative position of different parts of the object. And to detect such defects, we need to understand general context of the image, which can be challenging. And here you can see some examples of structural anomalies and logical anomalies. Okay, now we can talk about metrics. In our benchmark, we will calculate several metrics on image level, which is also known as classification task, and on pixel level, which is also known as segmentation task. And most popular image level metric in academia is the area under the receiver operating characteristic curve, AROC short, if I'm pronouncing it right, which measures the classification performance across multiple thresholds. We employ it as well to simplify comparison with other papers, but at the same time, we use practically oriented metrics, PG2 and PB2, meaning pre-sorted good and pre-sorted bad at 2% fixed threshold, which emphasize the practical applications of anomaly detection models by showing their potential to reduce human operator workload while maintaining an acceptable level of misclassification. I will talk more about it actually right now. So yeah, on this histogram, you can see two thresholds in dashed lines, and blue one shows good images with just 2% of bad images to the left of it. And this percentage of good images to the left of this threshold, pre-sorted, is the value of PG2 metric. And this similarly to the right one, bad images with just 2% of good images on the right of the threshold, it's the value of a PB2 metric, and we have used thresholds 2%. As discussed before, it is noticeably better than the human operator error rate could be. Of course, this number can be changed. We classified models based on the data we require for training, and most models require only good images. And although often they are called unsupervised, they cannot handle unlabeled data, as one of our experiments will show. We will use the name one class to emphasize separation from truly unsupervised models. And supervised models, as you can expect, require labeled data for both good and bad images. And there are two main issues with the evaluation settings used in academia. First one is the widespread use of the test set-based early stopping or selective reporting of best epoch result. As you can imagine, this leads to overfitting the test set and completely unrealistic performance estimates. And the second is the use of a center curve augmentation, which can introduce biases in performance evaluation by reducing the number of false positives. You can simply miss the defects if they are placed outside of the cropped area. So yeah, in our benchmark, we will use implementations with disabled both early stop and center cropping. And now I will continue discussing our benchmark. Yeah, so as discussed earlier, most of recent papers use one or two datasets which were both created in laboratory settings by manually damaging normal objects. And in our benchmark, we tried to include all known and solid datasets where defects emerge naturally on the production line. And here you can see some examples. We use mostly one-class models, which are the main target of both researchers as well. And again, they are trained on good images only. For the inference speed reasons, we focused on models which can run on consumer GPU, so no-diffusion models. We also do not test zero and few shot models which use a different training setting and fall out of the scope of the paper. We designed several experiments based on our experience to help close the gap between academia and practical applications. First, and probably the most important, we have evaluated multiple models on multiple datasets using unified setting. As mentioned before, no early stop on the test data, no center curves, also same input size, and same feature extractor for all the models. With this setting, we can, if you can see here, models from the year 2021 and 22 are still the best, namely patch core and reverse distillation, RD4AD, showing best results. And again, the models both are at least 3 years old. Recent GLASS beats it only on one of the datasets. And we also can see that results on the datasets with logical defects, MVTech loco, viaduct, VAD, are still quite low, which is an important thing to be aware if you are working with real-world applications. Defects like missing components or only shaped components are still hard to detect by open source solutions. And next, we look at how size of input affects the result. I think it's well known that bigger input is often better. And it was confirmed by many papers like MVTech ID 2 paper or maybe even Benchmark paper. And here you can see some visualization and our results. Also, quick explanation regarding heat maps on the left. If you have not seen them before, brighter color is supposed to predict the location of a defect. And you can see that only with the largest input size, the defect was somewhat visible. And we tested this on different data sets, so we can say larger input size, it's not always better. It actually makes detection of logical defect worse for some models like RD4ID or MMR. So yeah, you can find more results in our paper. For noisy label experiment, we compared three datasets with correct labels and with 4, 8, and 16% of good samples removed and replaced it by bad ones with the wrong label as good. And we can see how results are gradually getting worse with more mislabeled images involved for one-class models. It can be seen both at visualization on the left and in the results on the right. Only one truly unsupervised model in reach in the first row does not degrade with more noisy labels, but results are still too low for commercial applications. It can be a prominent direction for research as long as you use not only MVTech ID dataset. And data drift. Here we have two types of data drift. And again, to make it quick, we can say that models detect data drift as anomaly. You have different lighting, it is detected as anomaly. You have maybe different background, it can be also a problem. So it's important thing to be aware of this restriction. We also, since so many papers use test set for early stopping, we decided to do the same but with validation set, which seems more reasonable. And we took a supervised data set VAD, and we separated part of the training images into validation set. So it has both good and bad samples, and use this for early stop. And as you can see, even this way, results become noticeably better. And in this chapter, I will focus on the practical aspects here. And if you're interested, you can read recommendation for researchers in our paper. Data is always the most important part. Your model can be perfect, but it won't work if you have poor quality data. Let's start with this. First is the training data. Again, luckily, we need only good images for training. It's usually easy enough to collect, but it can be worth it to collect them over a longer period of time to catch some intra-class variability. And of course, make sure that labels are correct. As noisy labels experiment shown, poor labeling quality can make results significantly worse. Next is validation and testing, and here you need to collect bad images as well, and you also want to try to collect it over a longer period of time to capture variability of defects, at least to get some idea of what you can expect. And yes, please separate your validation set from testing set if you want to have a realistic idea of what your model can achieve in production. How to select model, and well, as our evaluation experiment shown, taking the best recent state of the art model can be a really poor choice. Appears that in the end you need to select between patchcore, RD4ID, and maybe MMR, glass, or CS flow. Patchcore is better if you have larger defects and you can increase input resolution to detect smaller ones. RD4ID can be a good choice for small defects, but with high resolution it might not catch bigger ones. And glass appears to be a good choice for rather simple defects, which can be generated using texture dataset, like scratches or pollution. Here is a bit more details about metric. If you wonder if 95 out of 100% of image or rock is enough, not necessarily. Here we can see the two top row metrics are image level rock and image level PG2, preserved good parts at a fixed rate of 2% of bad parts missed. And in green rectangle, we can see how MMR can pre-sort 63% of good parts with a rock of almost 94. And very close rock in the orange rectangle shows just 45% of pre-sorted parts. So we strongly suggest to use not only default metric. We have already discussed input size, but increasing this is probably the easiest way to improve your results using patchcore. I think we don't have time to dive deeply how this model works. But yes, there is many parameters you can play with to increase the speed of inference, things like this. And another trick which works the best for patchcore is to remove all the unnecessary part of the image, as the slide shows. Crop as close to the main object as you can, and if possible, you can even remove background, which will reduce number of false positives. And if you have model which is trained on more than one epoch, you can use validation set. Just please not testing. Okay, so just to round it up, as our validation experiment shown, models from the year 2021-22 still perform the best when evaluated on different data sets, so be careful with the recent SOTA models. Make sure your data is properly labeled. In contradiction to the widely used name unsupervised, most of anomaly detection models actually require strictly normal images for training. Use metrics which are meaningful for industrial tasks, and be aware of the data drift. You won't miss it, but at the same time, it can send a bunch of good parts to scrap if you have a different lighting or a new lens. A crop loss to the objects you're inspecting, increase the resolution if inference speed allows it. And finally, please do not use test and set for early stopping. It applies for both academia and industry. If in academia you just make your reviewer cry, in industry you can deploy something quite horrible in production. And many official code implementations do just this, so look at the code before running it. Although this is the more general life advice. Thank you for watching.